Welcome to Chemistry Solutions with Steve. This is a GCSE Combined Science Trilogy Chemistry Paper 2 Higher Tier, and it's from 2018. And you can download this paper from the AQA website. This video can be used by teachers who perhaps are not specialist science teachers or not specialists in chemistry, and obviously by students. Students, you can do this paper on your laptops, one question at a time. Stop the video, go back, mark your work and get instant feedback. Or you can treat it as a mock exam and sit down, do the whole paper in one go, on paper. The choice is yours. So we'll start with some general exam advice. You'll be given the exam and you'll be able to look at the front page and go through that front page before the examination continues. And what I suggest you do is go through each of the bullet points on the front page and you tick it when you've read it. You know, use a pencil and just tick each bit when you've read it. And that way you know that there's no information that's going to be any surprise. Another piece of equipment that you might find useful is a highlighter pen, and this will help you to highlight key words, command words, and number of marks available for each question. So I'll demonstrate this now. Question 1. Crude oil is a mixture of hydrocarbons. 1.1. The hydrocarbons in crude oil are separated into fractions by fractional distillation. Figure 1 shows a fractional distillation column. Crude oil vapour passes up the column. Complete the sentence and choose the answer from the box. And this is for 1 mark. The words in the box are condenses, dissolves, freezes, melts. Each fraction something at a different level. So let's quickly recap how a fractionating column works. The crude oil enters the furnace, turns the crude oil into vapours. It vaporizes it. These vapours rise and they separate at different levels. And the vapours separate because they condense at different temperatures. So, to get 1 mark for this question, you must write condenses in the space provided. Question 1.2. Now, why do the fractions separate? Tick 1 box for 1 mark. The fractions have different boiling points, different flammability, different melting points, different viscosity. Now let's go back to our previous question. We alluded to the fact that in the fractionating column, the fractions condense because they have different boiling points. So to get 1 mark for this question, you must tick fractions have different boiling points. Question 1.3. Most of the hydrocarbons in crude oil are alkanes. Figure 2 represents an alkane molecule, and it's one of those molly-mod models that you've probably seen at school. Name the alkane for 1 mark. Now, if we look at the first 3 alkanes in the series, methane, ethane, propene, the formulas are written there. So what we have to do is look at the photograph. Let's look at the black spheres. There are 3 of those, and they represent carbon. If we look at the white spheres, there are 8 of those and they represent hydrogen. So the formula is C3H8, which means that the molecule must be propane. So to get 1 mark for this question, write propane. Question 1.4. Methane, CH4, is an alkane. What is the general formula for alkanes? And tick 1 box for 1 mark. CnHN, CnH2n, CnH2n minus 2, CnH2n plus 2. Now this is a simple recall from your organic chemistry and it's the bottom one. So for 1 mark, tick the box at the bottom, CnH2n plus 2. 1.5. Alkanes burn in oxygen. Balance the equation for methane burning for 1 mark. The first thing we must do is balance the carbons and the hydrogens, and there's a correlation between the carbons and hydrogens in the alkane and the 2 products you always get in this reaction, CO2 and H2O. Let's take hydrogen first. There are 4 hydrogens. If we look at the water molecule, there are 2 hydrogens in water, so we must multiply that by 2. Now the carbons, if you look closely, are already balanced. There's 1 carbon in CH4 and 1 in CO2. So now we must go on to balance the oxygens, and we do this by writing out the individual molecules like this. So we've got our carbon and 4 hydrogens on the left. On the right, we've got our 2 water molecules, which is 4 hydrogens and 2 oxygens. So let's balance these oxygens. There are 2 oxygens in CO2. So altogether there are 4 oxygens on the right hand side. Simply to balance the number of oxygens on the left hand side, we put a 2 in front of the O2. Job's a good 'un. Question 1.6. Ethene is an alkene. Which reagent is used to test for alkenes? For 1 mark, tick 1 box. Anhydrous copper sulfate, bromine water, damp litmus paper or lime water. Now we know alkenes contain a double bond, and the way we test for that double bond is using bromine water. So to get 1 mark for this question, you must tick bromine water. Over the page, Table 1 shows data from a life cycle assessment, LCA, for the disposal of 10,000 biodegradable plastic bags. We'll come back to this table. Question 1.7. Why are life cycle assessments, LCAs, done? For 1 mark. Now this is a recall, and it's simple really, you've just got to remember it. Life cycle assessments are carried out to assess the environmental impact of products in each of the 4 stages in the life of the product. Question 1.8. Compare the 2 methods for the disposal of biodegradable plastic bags. Use information from Table 1. This is a 4-mark levelled written response. And the level 2 marking criteria are written here. So pause the video and make a note of exactly what you are expected to be able to do to get the full 4 marks. In Table 1 there are 3 categories or 3 descriptors: mass of CO2, mass of solid residue, mass of sulfur dioxide. And the 2 columns are burning and using the energy to generate electricity, and landfill. So we're going to directly compare the burning and the landfill. So for the mass of CO2 produced, burning produces 25, landfill 15 kilograms. So burning using electricity is producing 10 kilograms of CO2 more than landfill. That's a direct comparison. Let's consider the mass of residue. Burning produces 0.050 kilograms, whereas landfill 0.070 kilograms. So clearly landfill produces 0.020 more kilograms of solid residue. Finally, on to the mass of sulfur dioxide produced. Burning is 0.20, landfill 0.30, which is 0.10 more, or a 50% greater mass of SO2 produced. So by annotating the table, we can now take that information and construct our answers. And here it is. Burning 10,000 bags produces more carbon dioxide than landfill. In fact, it produces 10 kilograms more. Placing 10,000 bags into landfill produces 0.02 kilograms more residue than burning them. And finally, placing 10,000 bags into landfill produces 0.10 kilograms more sulfur dioxide, which is 50% more. Okay, over the page, question 2. This question is about the Earth's atmosphere. 2.1. Carbon dioxide is a greenhouse gas. What is another greenhouse gas? Tick 1 box. And this is a 1 mark question. You should recall that there are 3 greenhouse gases: carbon dioxide, methane and water. Looking at the choices, clearly choice number 2, methane, is the correct answer. Tick the methane box for 1 mark. 2.2. Greenhouse gases cause global climate change. Give 2 effects of global climate change for 2 marks. This is a bog standard. You've just got to learn these, and there are quite a few to pick from. Could have rising sea levels, extreme weather conditions, severe effects on agriculture and food production, melting ice caps, and the destruction of wildlife habitats. Pick any two for 2 marks. Question 2.3. 4.1 kilograms of a plastic used to make plastic bottles has a carbon footprint of 6.0 kilograms of carbon dioxide. Calculate the carbon footprint of one plastic bottle of mass 23.5 grams. And this is for 2 marks. Your answer must be in kilograms. The first thing we must do is try and find the carbon footprint per kilogram of the plastic, and to do that we do 6.0 and divide it by 4.1. We must then multiply that by the mass of one plastic bottle in kilograms, so that'll be 23.5 divided by 1000. Using our calculator, 6.0 divided by 4.1 equals 1.463414. We multiply this by 23.5 divided by 1000 to convert to grams to kilograms, and this comes out at 0.0235. Multiply 1.463414 by 0.0235 and you end up with 0.003439.024, and then we must do this to 3 significant figures. That ends up at being 0.00344 for 2 marks. Question 2.4. Give one way that carbon dioxide emissions can be reduced when a plastic bottle is manufactured. And this is a 1 mark. So to achieve 1 mark in this question, you could use recycled plastic bottles, which is a good way, or just use less plastic. That would get you a mark as well. Either of those for 1 mark. Question 2.5. Explain how the percentages of nitrogen, oxygen and carbon dioxide in the Earth's atmosphere today have changed from the Earth's early atmosphere. And this is a 6 mark question. This will be a levelled question. And here's the descriptor for level 3. Relevant points, reasons, causes identified, given in detail, logically linked to give a clear account. So again, this is one of those questions where you must plan. Jot everything down on the side in pencil and then you can rub it out later. Let's consider nitrogen first. Nitrogen has increased mainly because of volcanoes, but also of some denitrifying bacteria and the taking apart of ammonia. Oxygen, this is a bog standard reply. It's all about algae and plants. When algae and plants evolved, they started to photosynthesize. So photosynthesis uses up carbon dioxide and gives out oxygen. So this is why oxygen levels have increased over time as more plants and algae have evolved. Now, carbon dioxide levels have gone down, and again, this is partly due to photosynthesis because the plants and algae that evolved absorb carbon dioxide. Also, it's about sedimentary rocks and fossil fuels. Sedimentary rocks are formed from the shells and bones of sea creatures, and they build up over time to form limestone. Fossil fuels like coal are also formed from land-based plants that were rotted away over millions of years. Back in the oceans, plankton rotted away at the bottom of the oceans to form oil and gas. And all of this accounted for absorbing carbon in the form of carbon dioxide. So a levelled response would look like this. Nitrogen has increased due to volcanoes producing nitrogen and this building up over years. Also, some nitrogen comes from bacteria that evolve which can convert nitrates in the soil to nitrogen gas. Some nitrogen has evolved from the decomposition of ammonia. Oxygen has increased because algae and plants have evolved and through photosynthesis produce oxygen. Carbon dioxide levels have decreased because of photosynthesis as above, and it's used up carbon dioxide. This carbon dioxide has also dissolved in the oceans. This in turn has led to the formation of sedimentary rocks, like limestone, made from the shells and bones of sea animals. Also, plants have stored carbon dioxide in coal, and plankton has stored carbon dioxide in the form of oil and gas. Over the page, question 3. A student investigated the mass of dissolved solids in 5 cm³ samples of water. Figure 3 shows the apparatus. So you've got a beaker, Bunsen burner, tripod, what we might call a water bath, and a watch glass on top. Table 2 shows the student's result. Question 3.1. Calculate mass X in table 2. And here's mass X here, look. This is what you're going to try and work out. And this is a 1-mark question. Now X, this is the mass of dissolved solids in river water. And if you look here, what we've got basically, for those of you who are pretty clever at maths, is a factor of multiplication between 5 cubic centimetres and 1,000. In 5 cm³, there's 0.08 grams of dissolved solid. So in 1,000 cm³, there would be 0.08 times 1,000 over 5. And again, for those pretty quick mathematicians, that's a factor of 20. So crunch that on your calculator and you end up with a mass of X as 16.0 grams for 1 mark. Over the page, 5 cm³ is a small volume of water for each experiment. 3.2. Give one advantage and one disadvantage of using a larger volume. This is for 2 marks. This is one of those how science works experiments, isn't it? Question. An advantage of using a smaller volume is it will allow you to make a more accurate result. That's for 1 mark. For the 2nd mark, if you use a larger volume of water, it will take a much longer time to complete the task because you've got to boil all that water away. 3.3. Potable water is not pure water. Describe the difference between potable water and pure water. And this is for 1 mark. And this is just simple recall. You need to know what potable water is and what the difference is between pure water. And what we're looking at here is pure water is made up of water molecules. There's nothing else dissolved, no other substance is dissolved in the water, just molecules of water. However, potable water is not pure because it has dissolved substances in it. Do not mention potable water is safe to drink. 3.4. Potable water is obtained from both groundwater and seawater. Describe how groundwater and seawater are treated to produce potable water. And this is for 3 marks. So we're not looking for a long 6-mark answer. Keep it short and sharp. 3 points. Now we know groundwater does what it says on the tin, comes from the ground, so it'll contain bits and stuff, solids, so we need to filter those out. Once they've been filtered, that water needs to be sterilised so it's fit to drink. Now, to get seawater into potable water, we need to do something called desalination, and we can do this by distillation, or we can do it by something called reverse osmosis. So let's look at our answer. A suitable source of groundwater is filtered to remove any solids, 1 mark for filter. Then it's sterilised, 1 mark. The seawater is desalinated, that's the 3rd mark for desalinated. Over the page, question 3.5. The percentage by mass of dissolved solids in a 6.50 gram sample is 2.2%. Calculate the mass of the dissolved solids for 2 marks. This is a mathematical application. So what does 2.2% mean? It means it's 2.2 divided by 100 as expressed as a fraction. We need to find 2.2% of 6.50 grams. Of in maths means time, so we need to multiply 2.2% by 6.5. In other words, 2.2 divided by 100 times 6.5, and if you crunch that in your calculator, you get 0.143 grams. 1 mark for the fraction, 1 mark for the actual answer. Over the page, question 4. Fertilisers are formulations. 4.1. What is a formulation for 1 mark? Now this is a bog standard glossary item. You should know this definition. If you're not sure, make a revision card and learn the definition of a formulation. And a formulation is a mixture of a substance designed to be a useful product. So a mixture of substance designed to be a useful product, 1 mark. Question 4.2. A bag of fertiliser contains 14.52 kilograms of ammonium nitrate, NH4NO3. Relative formula masses are there. For the MR, the Mr, for ammonia is 80. Calculate the number of moles of ammonium nitrate in the bag of fertiliser. Give your answer in standard form to 2 sig figs. And this is for 4 marks. Now we start this question off with our formula triangle. Mr. moles with the mass on his head. If we're looking to work out moles, we cover the moles up and we have mass divided by the Mr. If we look in the question, the mass is the 14.52, the Mr is 80. So the number of moles is the mass divided by the Mr. So the number of moles is 14.52 divided by 80. That gives us 181.5. Now we need 2 significant figures, so that would give us 180. And then if we want to put that into standard form, we have 1.8 times 10 to the power of 2. So we get 1 mark for the formula, 1 mark for subbing in the numbers, 1 mark for the raw answer before standard form and before significant figures, and then the final mark goes to the final answer in standard form. Over the page, question 4.3. The fertiliser also contains potassium chloride. Explain why potassium chloride has a high melting point, and this is for 4 marks. Let's get some ideas down. Potassium chloride is an ionic compound. Therefore, it has a giant lattice structure, a giant ionic lattice. Therefore, there are very strong forces of opposite electrostatic attraction between the positive and negative ions, potassium and chloride. So when we come to melt it, we have to supply a lot of energy to overcome these very strong bonds. So let's put all this together to get ourselves a 4-mark answer. Potassium chloride is an ionic compound, therefore its structure is a giant ionic lattice. This means that there are very strong forces of opposite electrostatic attraction between the ions. We call these ionic bonds. These strong bonds require a lot of energy to break them. Now let's look at the mark allocation. We need 1 mark for saying it's ionic, 1 mark for a giant lattice, 1 mark for some sort of forces or particularly ionic bonds is good, and then the final mark, lots of energy to break them for our 4 marks. Please note as well, underlined phrases which we need to put in order to get that explain mark that's the command word in the question. Over the page, question 5. A student investigated the effect of the size of marble chips on the rate of the reaction between marble chips and hydrochloric acid. This is the method used. We're not going to go into detail, we don't need that. We'll be coming back to this later on. Figure 4 shows the apparatus. Ditto, we'll come back to question 5.1. Complete the equation for the reaction. And this is a 2-mark question. So there's some recall of acids. So you should know that a carbonate and an acid will give a salt plus carbon dioxide and water. All we've got to do is find out what the name of the salt is. Salts are always named with a metal element first, followed by a non-metal. So the metal element is the calcium coming from the calcium carbonate, and then the chlorine or chloride coming from the hydrochloric acid. That gives us calcium chloride, and we remember that calcium is in group 2, so it has a 2+ charge, so we need 2 chloride ions to make it balance. So we've got CaCl2 plus CO2 plus H2O. Now all we've got to do is balance it, and the trick to this is to write out the individual elements below. So this is what we've got here. We've got the individual elements expanded up to show how many atoms there are in the molecules. So if we look at calcium, we can check that off. There's one each on either side of the equation. One carbon, we can tick that off as well. There are 3 oxygens on the left, and here we are, 3 oxygens on the right. Let's look now at the hydrogens and the chlorines. We can see there are 2 hydrogens there and 2 chlorines there, but only 1 hydrogen and chlorine on the left-hand side. So we need to double that up, and that's what we call balancing. So we put a 2 in there, and that's our 2-mark question. So over the page, figure 5 shows the students' results. And here's figure 5. It's a typical graph, isn't it? We've seen these many times before. The graph has got the volume of gas produced on the y-axis and the time in seconds along the x. 5.2. Describe the trend shown in figure 5 and use values in your answer. And this is a 3-mark question. If we go back to the graph, we can change that. We can look at that graph and we can divide it into 3 distinct sections. The steep curve, then it's curving a bit more, and then there's a flat bit. In the first section, the volume is increasing fast, up to about 10 seconds. In the second section, 10 seconds to 30 seconds, the production of gas is less rapid. And then in the final section, number 2 to 3, between 30 and 40 seconds, there's no gas whatsoever. Now let's put this into our written answer. The rate of the volume of gas produced is quite fast. Between 0 and 10 seconds, between 10 and 30 seconds, the rate of production slows down. Between 30 and 40 seconds, there's no gas produced. As long as you've got some numbers somewhere, either time or volume. 5.3. Describe how I would use figure 5 to find the rate of the reaction at 15 seconds. You do not need to do a calculation, and this is a 2-mark question. Now this question is about drawing a tangent. Now there's a little mini graph here, and I'm going to show you and remind you how to draw a tangent. You draw a construction line up at the time 15 seconds, draw a line across where the curve is on 15 seconds, and then once you've done that, you work out the gradient of that tangent. So to get your 2 marks, draw a tangent line at 15 seconds, calculate the gradient of the tangent. Remember, no calculation required, 2 marks. 5.4, give the units for the rate of this reaction for 1 mark. So we're going to go up to the graph for this. The volume of gas is in centimetres cubed, circle it there, and the time is in seconds. So the units for this are going to be centimetres cubed per second. And it must be cm to the power of 3 little s. So, table 3 shows the results of the investigation. And here's table 3. You've got the relative size of the marble chips down the first column, and then across there, the volume of gas produced every 10 seconds. Give one conclusion for 5.5 about how the size of the marble chips affects the rate of reaction, and this is for 1 mark. So let's look at the first column. The relative size of the chips is increasing as we go down. If we look at the first set of results on 10 seconds, the volume of gas produced is decreasing. So in order to get 1 mark, we can say as the relative size of the chips gets larger, the rate of gas production gets smaller or lower. 5.6. Suggest why all 3 sizes of marble chips produce a maximum volume of 60 cubic centimetres of gas, and this is for 1 mark. Let's go up to the method, and we can see that you are adding 10 grams of marble chips and 50 cubic centimetres of hydrochloric acid for every single experiment. So we can say in the method there was the same mass of marble, which means the same number of moles, and the same volume of acid, which also means the same number of moles. So the same number of moles of acid and the same number of moles of marble are going to give you the same volume of gas. Question 5.7. Figure 6 shows 8 small cubes, each 1 centimetre by 1 centimetre by 1 centimetre, and one large cube 2 centimetres by 2 centimetres by 2 centimetres. Calculate the surface area of the large cube for 2 marks. The surface area of the cube is going to be the surface area of one side multiplied by 6. Now we can see the dimensions of the large cube. It's 2 centimetres by 2 centimetres by 2 centimetres. So one side is going to be 2 centimetres by 2 centimetres multiplied together to get the area. So the area of one side is 4 centimetres squared. Times this by 6, and the surface area of the cube is 24 square centimetres. So we'll get 1 mark for working out the surface area of one side, and then another mark for the total surface area of the cube. Point 8. Explain why the size of the marble chips affects the rate of reaction. Give your answer in terms of collision theory, and this is for 2 marks. Now, if we go back and have a look at the diagram above, we can see the total surface area of the small cubes is 48 square centimetres. We've just worked out that the surface area of the large cube is 24 square centimetres. So the surface area of the small cubes is greater. It's actually double. So in collision theory, that means there is a greater surface for the collisions to happen between the acid and the marble. So for our 2 marks, the smaller chips have a greater surface area, therefore more frequent collisions. Question 5.9. The student repeated the investigation with small marble chips using hydrochloric acid of a lower concentration. Figure 7 shows the volume of gas produced during the first 40 seconds. So again, you may well have done this as a required practical. You've got a graph with the volume of gas and the time. The thick line is the higher concentration, the dashed line is lower. Explain why the results for the lower concentration of acid are different from the results for the higher concentration of acid, and this is for 3 marks. Let's make some notes on the graph. Here's the higher concentration. We'll use that as our starting point. The first part of the graph here is much steeper. And that means that if it's steeper, the reaction is going faster. Now, if the reaction is faster, there must be a reason for this. And this is again due to collision theory. The reaction is going faster because there are more frequent collisions. Why are there more frequent collisions? Because the more concentrated acid has more particles or more hydrogen ions in the same volume. So to get our 3 marks, the first part of the graph for the more concentrated acid is steeper, so the reaction is faster. This is because there will be more successful collisions, mark 2, due to the higher number of H+ ions per unit volume. Now look at these key words I've underlined. These are the words we need to be using in order to get our explain bit for 3 marks. 6. Bleach is a solution of sodium hypochlorite. Chlorine gas is produced when bleach reacts with hydrochloric acid, and there's the chlorine gas. 6.1. Give the test and result for chlorine gas. You should know these tests, these gas tests. You've just got to learn them. If you don't know them, make a revision card. So, in order to test for chlorine gas, we must use moist or damp litmus paper. That's the test. Result, the litmus paper is bleached or goes white. 2 marks. Point 2. Figure 8 shows a sealed flask of sodium hypochlorite and hydrochloric acid. Notice the stopper at the top. Question 6.2. Explain why equilibrium is reached for 2 marks. So this is the definition of equilibrium. When a reversible reaction occurs in apparatus which prevents an escape of reactants and products, it's called a sealed or closed system. Another key factor of equilibrium is the forward and reverse reactions continue at the same rate. So to get 2 marks, at equilibrium the forward and reverse reaction continue at the same rate, and this must be in a closed or sealed container. 6.3. The stopper in figure 8 is removed and hydrochloric acid is added. The stopper is replaced. Explain what happens to the equilibrium for 4 marks. So when you add a reactant to an equilibrium, the equilibrium will shift towards products. So therefore, the equilibrium is shifting towards the right-hand side. So if the equilibrium shifts to the right, more product is made. Now as the stopper is replaced, the new equilibrium will be established. So let's look at constructing our 4-mark answer. When you add hydrochloric acid to the flask, you add a reactant. When a reactant is added, the equilibrium shifts towards the products, the right-hand side. So there's your 2 marks for that. Now as the stopper is replaced, 1 mark, the more product will be formed and a new equilibrium will be established. Over the page, chlorine gas is also produced when hydrogen chloride decomposes, and there's an equation there. The forward reaction is endothermic. 6.4. Predict the effect of increasing the temperature on the amount of chlorine gas produced at equilibrium. Explain your answer using Le Chatelier's principle for 2 marks. So the forward reaction is endothermic. Increasing the temperature on an equilibrium shifts the equilibrium towards the endothermic. So that means it's going forward, so that means there's more chlorine gas. So to claim our 2 marks, the amount of chlorine gas will increase because if the temperature is increased, the equilibrium will always move in the endothermic direction to counteract the change imposed. And that is Chatelier. And now to the final question, 6.5. Explain the effect of increasing the pressure on this equilibrium for 2 marks. So let's go up to the original equation. We can see here that we've got this equation, and on the left hand side there are 2 molecules of hydrogen chloride. On the right hand side there's 1 molecule of hydrogen, 1 of chlorine, making 2. So the numbers of molecules on each side are the same. So for our final 2 marks, there will be no change in the equilibrium because when there is an increase in pressure, equilibrium will move towards the side of the reaction that has the least number of gaseous molecules. Both sides have the same number of molecules, so there is no change.